Hello, everyone. My name is Shiv Bansal, and I'm honored to speak at the 2025 Global Health Leaders Conference at Johns Hopkins University. The title of my presentation is Illuminating Resilience, Engineering Cyan Thermally Stable Fluorescent Proteins. Today, I'll be sharing how I engineered a fluorescent protein that resists both heat and acid, which is a step toward making diagnostic tools more reliable in real-world global health conditions. This research was conducted with Missouri State University and published in a peer-reviewed academic research journal, Wiley's Protein Structure, Function, and Bioinformatics Journal. I am a rising senior at Kickapoo High School in Springfield, Missouri. I am passionate about translational medicine, where discoveries in the lab can become tools that help people in the real world. Outside of school, I served the American Red Cross nationally as a youth and young adult ambassador. This project began from my curiosity about how things glow, but turned into a chance to solve a global health problem. Being published showed me that this science wasn't just solid, it was very useful. Now, let's zoom out for a moment and discuss the basics of fluorescent proteins. Fluorescent proteins glow under certain light and help us detect things like viruses and cancer. They are essential tools in diagnostics and lab research. But fluorescent proteins, especially cyan ones, are fragile. They lose their glow when it gets hot or acidic, which is exactly the kind of environments found in tropical clinics in disaster zones. Imagine testing for cholera in a flooded village or malaria in a clinic with no refrigeration. If your fluorescent protein fails, so does the diagnostic test. So we asked, can we engineer a cyan fluorescent protein that keeps glowing, even in an environment with excess heat, acid, or overall instability? To explore that question, we started with a naturally heat-resistant protein called thermal green protein, or TGP. Using site-directed mutagenesis, essentially molecular editing, we made targeted changes or mutations to shift TGP's glow from green to cyan. From there, we adjusted specific regions of the cyan protein to improve both brightness and stability, eventually creating our final version, CTP 1.0, which is a cyan fluorescent protein that can survive heat, acid, and other harsh conditions. Then we tested CTP 1.0, our final product, against the current gold standard in biomedical research, a cyan fluorescent protein called M-turquoise 2. First, we took a look at pH stability of each of the proteins in different pH environments, namely CTP 0.75, CTP 1.0, and M-turquoise 2. From figure 2D, we found that CTP 1.0 glowed even at an acidic pH of 3.5, while M turquoise 2 faded, which was a critical observation for us in acidic environments like inflamed tissues. Next, we took a look at chemical stability, as shown in figure 2H for each of the proteins. From the figure, we noticed CTP 1.0 withstood a concentration of up to 4 molar guanidium HCl, which is a harsh chemical denaturing. Additionally, from the figure, we found that CTP 1.0 outperformed earlier CTP versions when HCl was added and performed very comparably to M turquoise 2. Then we took a look at the thermal stability of each of the proteins as shown in figure 2L. From this figure, we saw that CTP 1.0 stayed brighter longer in elevated temperatures, as well as for elevated time periods compared to other proteins, which is ideal for field diagnostics without refrigeration. So we saw that across acid, chemicals, and heat, CTP 1.0 kept glowing. But that raised a deeper question for us. Why was CTP 1.0 so stable? To find out, we had to look inside the molecule at its structure. That meant generating structural data. To generate that data, I spent last summer growing crystals of CTP 0.5, which is an earlier version of the cyan fluorescent protein, through optimizing buffer conditions, which was a tedious but very essential step in our research. Once those protein crystals were formed, we exposed the crystals to X-rays. The diffraction patterns formed from the X-rays were analyzed using a reference structure called monomeric Azami green, or MAC, which allowed us to generate a 3D electron density map of CTP 1.0, shown on the right-hand side of this slide. This map revealed a key hydrogen bond between position T199 and the chromophore in CTP 1.0, which is the glowing part of the protein. It was like a molecular seatbelt holding the core together. This single hydrogen bond helped explain CTP 1.0's unusual resilience and gave us a design roadmap for future improvements. And with that, our research brings us to the bigger picture. Why does this research matter for global health? Because even the most advanced technology is useless if it fails where people need it most. To be useful in diagnostics, a fluorescent protein must be bright, chemically and thermally stable, acid resistant, and functional in low resource environments. And guess what? CTP 1.0 meets all of these criteria. It can help power biosensors in rural screenings, drug trackers in acidic tissues, and diagnostic kits in refugee camps and disaster zones. By publishing this protein, we're advancing health equity by creating a tool that's durable, accessible, and ready for real-world impact. But for me, this project wasn't just about proteins. It was about what it represents. What stood out to me in this project wasn't just the science. It was the sense of possibility this project unlocked. It showed me that scientific impact doesn't have to wait for med school or policy work. It can start in a high school lab with the right question. From one hydrogen bond, we created something that someday might improve diagnostics in the world's hardest places. And now this protein is published research and ready for others to build on. And what is my hope with this project? That other young scientists will ask themselves, what can I build that the world truly needs? Here are my references. I would like to give a heartfelt thank you to Dr. Natasha DeVore at Missouri State University, my mentor and co-author. Thank you also to other students who worked on me with this project, and to the National Science Foundation for supporting our research. And to all of you, thank you for your commitment to global health. If you have any questions or would like to connect, I would love to continue this conversation. My email is as follows. Thank you so much for your time and attention.